Okay. So we have presentation presenting quotes.
Okay, oh yeah, line with the rods. Okay, yeah. I was trying to have a CS. Yeah, that's why I'm best.
Excellent. Let's go there first. So, and you will fast forward it, or do you want? I can just do it. The speaker.
So you're left on side. So in this combination of late nights and jet lag, jet lag, very late. You only have to have
Shall I begin? Sure. Okay, so we'll begin the presentations. We have now about 90 minus 10, so 70 minutes for 4 speakers. So I don't know, of order 14 plus maybe 13 plus 3, something like that. I think it was supposed to be at 10 plus 2, but since we have a little bit of extra time. So the first speaker was supposed to be Noemi, but we'll start with Leonid Gurvits, who's going to talk about the extraterrestrial extension of the ngEHT. Sorry.
Thank you very much. It's a great pleasure to give a talk, number 1, at this session, which is supposed to be concerned with this sighting, right? So it looks like we're certain about the sighting space. That would be my main point. Where is it? Something. Well, I can do it from here.
Yeah, this is close.
All right.
Yeah. I can do it if you want.
No, it's
You
okay.
You can send it from here.
Right. Okay. First of all, let me start from the simple statement. In my opinion, while dreaming about new astrophysical tool, it is essential to pick up at least one or maybe several major parameters of this tool, which would be significantly better than anything expected. Or anything available and projected to the future. Now, this meeting is concerned with ngEHT, for which, of course, angular resolution is one of such parameters, if not the main one. So let's dream how to push the envelope of angular resolution. As the main parameter for our future millimeter and submillimeter facility. Let's remind ourselves that by now, EHT demonstrated imaging capability with angular resolution of 20 microarc seconds, well known to everybody here. And then Radiastron Space Wheel Bear mission achieve more or less the same angular resolution with some caveat, and of course, a very different frequency. And here is one of recent publications with very nice image of the source OJ287, published by, well, several people present here in this audience, Talia, first of all. Here are the examples of the state of the art for today. Now, if we dream to go to even higher angular resolution, what do we need to do? Well, we need to exceed the baseline available on this wonderful planet, but you cannot get more than 10,000 kilometers, right? So if you want to go to high angular resolution at a fixed wavelength, you have to increase baseline, therefore you go in space. Or if you say, all right, I go to shorter wavelength and I use maximum baseline as available on this planet, Well, this is HT or ngEHT, but there is a problem. You cannot go to much shorter than 1 millimeter wavelength because atmosphere. So to beat atmosphere, you go in space. So no matter what you do, you still have to be in space. And this is the main driver for dreaming about interferometry in space. And of course, if you combine two approaches, baseline, longer than Earth diameter, and wavelength, shorter than the atmosphere limit, well, that would be even better. You just combine both these benefits. By the way, this also a major factor for improving astrometry, not only for imaging experiments. So to beat Earth imposed limits, we need to be in space. What about heritage of this sort of exercises? In terms of VLBI in space, there were 2.5 missions, 2 dedicated missions. The first one, VSOP, Japanese-led, and the second one, Russian-led Radiostron. But before these 2 dedicated missions, there was orbital VLBI demonstration experiment in the middle of 80s TDRAS. In all 3 cases, fringes obtained very reliably on all baselines. In the case of Radiostron, going all the way to the moon, so something like 25, 30 Earth diameters. So space VLBI and fringes in space are, let's say, under control in principle. As for going to millimeters and sub-millimeters, the situation in a sense is even better. There were many missions, many of them successfully completed. Listed here, SLOS, Rodin, Herschel, Planck, you name them, there are many of them. And there are several concepts which are still in the drawing boards or in preparation, like 2 mentioned here. So there are many work in this area. Why not to combine this? That was the idea behind why it's stuck. Yes, right. Okay. 3 years ago, European Space Agency issued call for ideas, for proposals for ideas, and this is important wording, not for projects, for ideas, to form a program, major ESA science program called Voyage 2050. 2050 years is of course a year, not my graduation exactly, but 2050 is sort of envelope, a target envelope. There were many proposals in response to this call. One of them was our proposal called TESA. And here is acronym shown on the top in yellow. So this is bottom-up approach in which we suggested a mission which would do VLBI at millimeter and sub-millimeter wavelengths. I can tell you right away that we had no ambition to be immediately picked up by ESA for implementation, but it was considered seriously. You can find references on this white paper in ESA documents defining Voyage 2050. As a benchmark, we considered as case study published several years ago by, again, several people, several co-authors here in this audience, and first author, Frank Roloffs, known to many of us. Here are main parameters of that mission, consisting of several, 2 or 3 spacecraft. This mission, as well as TESA in general, was conceived as a multitask facility, more or less, let's say, global VLBI in space, but operating at millimeter and sub-millimeter wavelengths. However, we considered different science cases, which I will skip now because I have no enough time to do that. But the important thing was for us to pick up one science task which would help us to define major specifications of potential mission. And as such, we decided to focus on the case already shown several times at this workshop. This is study of photon rings and subrings. Here is a picture from this publication by Michael Johnson et al. I will already discuss several times here. In order to study photon rings in details, several orders of photon rings in details, it is essential to get to UV spacings somewhere here where the upper envelope of this very characteristic pattern of UV response on photon rings would be clearly visible. Now, on the lower part of this diagram, you can see the dependence of baseline length and frequency, with all these straight lines showing different characteristic sizes of interferometry. Obviously, to address this area of UV pattern, you have to be somewhere here. And no matter what sort of realistic frequency you do on the ground, the size of the Earth is somewhere here, below 10,000 kilometers. No way it can be done on Earth unless you jump to unrealistic frequencies. So you have to be in space, somewhere here. The question is how to get there, how to do this sort of science. Again, the same picture, and here we put straight lines which correspond to hypothetic mission, which we call here TESA, and we consider several cases, very simple calculations here for 4 frequencies, from 220 gigahertz, like ngEHT does today, 345 ngEHT soon, or ngEHT, and 2 other frequencies which are not reachable on the ground. This is the range of UV spacing which is needed to address this science. So how to do this? We need to operate, say, at these 4 frequencies with baseline sensitivity. Well, it will be shameful to be less sensitive than what is available now. So let's take as a benchmark sensitivity of projected ngEHT, which primarily depends on the size of telescope. So 10-15 meter single antenna in space, and bandwidth 16 gigahertz as a minimum, which corresponds to 32 gigabit per second, or of course wider if achievable. The question is it possible actually to do this thing in the foreseeable future? Well, I cannot give you a simple answer, yes or no. If you are interested, look on this paper, which we published just a few weeks ago, but some hint on the answer are actually go back for 40 years, well, 35 at least. Strangely enough, in the second half of 80s, ESA conducted a study called IVS, International Veil Satellite, and it was done with the involvement of European industry. You can see major table from this mission description with 220 gigahertz shown clearly. And here, look what was the goal in terms of fringe spacing, 1.4 microarc second. Well, it's exactly what we need. And the size of the antenna was 25 meters. So what we're talking today is not actually that crazy. People are dreaming about that for a long time. And as usual, most new things are well forgotten old ones. There was another study based on, do you recognize this? This is the largest piece of space debris, in my opinion. So this piece of hardware costs 10 to 10, something like that, dollars. Terrible price, doing, well, not much. But in the end of the 90s, there was an interesting study conducted by Aerospatiale, now it's part of Airbus Defense and Space, where they considered this station, International Space Station, as an assembly base for something big. And there was an idea to use it to build X-ray telescope and some other structures, and we injected something as well. So they considered whether it's possible to assemble large antenna and then to push it gently out of space station, making free-flying radio telescope. Well, there are many difficulties in doing large structure attached to ISS, but it is not hopeless, especially if you combine 2 technologies. large structure in space. And this antenna, perhaps known to many, originally called amoeba, now it's named to YTLA. It's an array which is operated by Institute in Taipei, 13 antennas. So this sort of structure would look perfectly well if fitted there. And the advantage is that it can be assembled one by one. So you launch or you assemble there only a manageable piece of hardware, sometimes several meters in diameter, and then you achieve what you actually want to do. Now, there are many advantages of doing this step by step. I will not go into details, only to remind that again, the idea of infinitely expandable antenna in space is pretty old. And to do so, you need a base in space, and importantly, not operational site. Don't do operations at the assembly site. Assemble satellite with antenna and then push it away to operational orbit. It can be done with low thrust, no danger of loading the structure beyond the limit. And by the way, it can be done stepwise, starting from 7 elements, 1937, you know, these fancy rounded numbers there. A single antenna can be copied from the one used for Herschel. Now, this is not the only case of addressing photon ring science in space. TESA was sort of Europe-centric, mostly proposed by people from Europe. By the way, I missed on the first slide that there are many people, you can see slide later on, many people from TESA team, mostly European, but there is another team which proposed something rather opportunistic called Saltus. This is a sort of piggyback on single aperture large telescope for studies in space. This is run by people from Arizona University. The main feature of this project is a single dish, for now inflatable, or able to operate at frequencies more or less like ngEHT. This is single spacecraft approach, and the baseline will be between spacecraft and Earth. The main science, one of the science drives is exactly the same as I discussed several minutes ago about TESA. Here is the orbit with different fraction of the orbit dedicated to different size. And there is even study of 14-day orbit, which would allow to achieve reasonable UV coverage with just single baseline using this large antenna in space. Now, to make this all things realistic, you have to address many engineering trade-offs. Some of them are listed here. I'll not go one by one here, only to, but yeah, I only will mention that this is a typical case when talking about facility which really pushes the limit. And that's exactly what we need to do science which will be truly transformational. This picture is taken from the study we conducted several years ago with UV coverage achievable by just single baseline between two antennas on medium Earth orbit satellites. So my task today, as I saw it, was just to show that it is not hopeless to work toward creation of a facility which would be able to address science which can be done only by means of long baselines, longer than Earth diameter, at wavelengths shorter than permitted by Earth. It is becoming realistic. It's not as crazy as it might sound. So I would like to finish with this slide, which is just a dream, of course, to have a constellation of antennas in space. But again, the main message is that it is not impossible. to work on a mission of that sort now. Thank you very much.
Hi, my name is Janice, and I apologize that we have not met first, but I take a little bit of exception to your comment about International Space Station, and since I've worked on International Space Station for a majority of my career, I would like to address the remark that not much is happening there. I think that there is a need in engineering feat and collaboration of 17 countries, and I actually think it's a very good model for ngEHT in some ways, in that fact it was something that was built over a large time frame and had to be operated incrementally while in development, and that's a very good model for ngEHT. And I had some other points with respect to the antenna diameter size. It's really important to keep in mind the payload fairing diameter, because that will always be your limitation, and not necessarily be your weight. It may actually be your lightweight structure. And three, I think the creativity and the designs are great. And I think actually mentioned space would be a fantastic application, because when you justify a space station, you really have to show that it has something unique that you cannot have done on Earth. So I love the direction you're going.
Thank you very much. I first of all, apology for being too harsh about space station. I can tell you that's the wireless training. So I know what is it very well. And my point is not that ISS as such can be used as a facility to assemble example. And example based on the study conducted by
Ming didn't send me the slides.
opportunities of assembling something big in space.
Is it here? Is it in this room?
And
Is it in the one?
it's not
Sorry?
right? It could be some other options which might be considered. Maybe even without but assembling in space large structure.
Okay, it's okay.
And that is something. Thank you.
It's
About disturbing the Earth observations, starting is a lot of resistance to telescopes in space. How big will these structures be? And how big will they be? I mean, in terms of disturbing Earth-based observations.
You should mirror your screen because if
Overcrowding.
in the Zoom we see this desktop.
Really?
Seeing it here is my laptop.
Okay, perfect. How can I do this?
Go to number where is display.
Okay, we'll have time for 2 more questions, please. Okay, please go ahead.
Well, we prefer the orbit part, but maybe something like.
Is it different now because it's a question?
Mirror.
At this point, it's there are advantages
Now
of
you can see.
or
Yeah, no,
there are
the same
some
screen.
Okay,
practical
okay,
advantages
excellent.
to make that presentation.
There are interesting
Here.
tasks which can be addressed at L2
Excellent.
Earth moon orbits. So there are different things. This is not the principal limitation. We are now working on detailed simulations on L2 Earth moon, not Earth sun, Earth moon. Anything goes with it. There are no practical limitations. And again, if you assemble something on the low orbit, then there is no problem to place this new structure on another orbit using low thrust engine, so without high acceleration. It will take several weeks, a month to reach a very simple orbit.
So what will be the expected lifespan of the telescope? We
And
need to
expected
determine lifespan. Yeah, the mission period, something like that. Because we need to determine its position.
Oh, like that?
Yeah.
Well, there are examples of science hardware working tens of years in space. Voyager, for example, works already almost half a century. In terms of closer examples, well, of course, Hubble, but of course, yeah, Hubble was service. But Radiostorm worked successfully for 7.5 years, for example. So I think that having some like 10 years operational is rather realistic.
Yeah, and it depends on whether or not you have propulsion. So XP, for example, has no propulsion on board, it'll possibly re-enter, it has a lifetime of 18 years. But that becomes part of the design space. But 20 years, if you look at Sgr A, if you look at Hubble, 20 years is not unrealistic.
Just maybe a silly question. Have you thought about the moon observatory? So is it more expensive than a spatial one?
Yeah, we did a lot. But there are no obvious advantages, especially at short wavelengths. At long, maybe because of interference. Human-made interference, if you are on the far side, you are shielded from us, from all this stuff which is in our pockets. As for EHT-like frequencies, there are no obvious advantages of being on the moon compared to free flyer. And on top of that, you have to remember that accelerating to the moon costs you the same amount of delta V or engine as decelerating. So you pay too fast. So that just go there.
Thank you.
Thank you.
The next talk will be from Dr. Ming-Tang Chen on behalf of AJA on the future of the Greenland telescope.
I'm gonna add this mic because unless that is the. Sorry, Ming-Tang, just a second.
It's okay.
About 15 minutes or so, that's fine for questions, or we can watch the trial.
Okay. I'm Ming-Tang Chen. I'm from Asia in Taiwan, but I'm based in Hawaii. So we've been building this Greenland telescope in the past 12 years now. So let me talk a little bit about our operation status right now. So currently we are in. Okay. First of all, I'd like to. This is a collaboration project between AJA and Smithsonian. Recently, we have a new partner. This is Niels Bohr Institute. That's welcome them to join us to build this telescope observatory on the Greenland ice sheet. Now, how do I turn it? Okay. I'm going to quickly go through what the status of it. So currently it's sitting in Thule. Thule is U.S. Air Force Base. It's near the sea level, but it's winter is very cold, extremely cold. I mean, so cold that we can do 230 gigahertz. So we have been since 2018. We've been up in observation with 86 gigahertz, 230 gigahertz. We also have the fringe verification at 345. So we've been part of the EHT telescope GMBA observation in the past several years. In the past 2 years, during the pandemic, the travel is very limited. So we got into this remote operation. So pretty much the telescope, we can operate it remotely. Remotely meaning that Satoki was sitting in the dormitory drinking his beer, but then the telescope was sitting on the side of the runway, and we operate it through the internet. Now, current problem to operate it even say like from Taipei or from Cambridge is because the internet connection is really no good right now. We're hoping that when this OneWeb or Starlink operational, then we should be able to do a really remote operation. But this is the model we're going to do when we move on to the ice sheet. So Thule at this moment is our staging areas, but also for testing our operation. It's cold enough for us to test everything because we pretty much changed, retrofitted a lot of important components of the telescope from the LLAMA prototype. So as far as we know, everything is working. It's ready to be moved up to the IC. So we've been in preparation for the summit deployment. Yeah. So in this meeting, this first time I learned about the ngEHT, the project, the proposal, that which remind me when we started this whole project back in 2008, 2009. At that time, we recruited Srinivasan and also KG Asada to our institute. We wanted to start a DLBI. We know that the sub-millimeter DLBI is going to be a hot topic, so we wanted to do it. So the first thing to do is that we want to find a site, but because we've been operating the sub-millimeter array and also the LLAMA, we know the importance of the site. The first thing we do is that we have to locate a site. First thing is look at the satellite map. We identify, look into some dry site in New Zealand, and that is really too low. It's only a few hundred meters in altitude. We also look into some mountain top in Alaska, but there's no way to get up to there other than helicopter. South Pole is pretty good, but South Pole is already there's a telescope. And then we found out is the Greenland. Greenland is very dry, so we just Google it, any facility in Greenland, and then we found a place called Summit Camp. We just write email to the people that live there, and it turned out to be a camp operated by the NSF, and that's how we get everything going like this. The first thing we do is that we bought this commercial this radiometer. This is making sure the site is what we wanted. That's the most critical, because without the site, it's very difficult for us to design, specify our what we want to build, especially the telescope. So instead of developing a new radiometer, we just purchased it. It's 150K, and then we calibrated on Manuel, calibrated first in the lab and the Manuel to make sure that everything is okay. Before we move it to the summit, and we found another site. That's a site. It's called Eureka in northern, also in the Arctic Circle in Canada. It's the site is about 600 meters. We moved the machine there to test it for winter, and then ended up moving to summit, and we get a 3 years data. Actually, for the first winter, we already knew that it's an excellent site. So actually, before we get our hands on the telescope, which is the LLAMA prototype, we already knew that this is the place we're going to go. And from there, so we know that we can proceed to produce a clear definition, a specification of what we want to do. So the point I try to make is that the new sub-millimeter site is very difficult to come by. We are aiming, our project, we aim to do a terahertz observation, but I think we ended up with what we can only do 690 gigahertz. Our dish is simply not to be terahertz level. So we also identified the Greenland summit as excellent sub-millimeter site. It's better than, I think from our data, we believe that it's better than Mauna Kea, slightly worse than South Pole. Currently in Thule, we can operate 230 gigahertz in okay opacity. 345 is doable, but weather has to be weather permitted. In the rare, has to be very in a deep winter, very cold weather. So looking for a site is difficult for some millimeter. Looking for a bunch of sites is even more difficult. So we also, I think, we benefit. Well, our team is not coming out of the blue. I'm showing this is not because I want to brag, but it's just try to tell you that we started with sub-millimeter array. Our team in Taiwan, we built 2 telescopes and actually deployed to Mauna Kea. Later on, we do this. I mean, you just saw that amoeba telescope from the previous speaker. Later on, then we are part of the ALMA. We built the front-end integration center and a whole bunch of other stuff. Ranjani here is also participating in one of the projects. Then later on, we built this. Even when we built this, do all the retrofitting, moving from Sapporo all the way to Thule, it is still very difficult. But our team has been, the entire team is the same team from the SMA all the way to ALMA to Greenland. We have a very good industrial partner. For example, the antenna itself is Greenland telescope antenna is made by Vertex, that's a German company. We've been working with them since the amoeba time. So we know each other, and this really have know what we are. Well, they're expensive, but they're pretty good, like everything German made. Also, we are local Taiwanese industry that's helping us all the way since 1995 during the SMA. So that's the team, that capable team that we work together. We also got help from NIO and ALMA. So the point is that you need an experienced partner. I think that's everything else. This is the I was trying to tell. I was talking to Aaron that this is a radio astronomy instrumentation is a niche. It's a niche kind of work. Yes, experience is very important. And then come to the receiver part. Sub-millimeter receiver is not like I think my experience is that usually you need a receiver team for doing this. Well, like Iran, they have this they will have their own receiver team. For SMA, it's the same thing. There's a receiver lab. For us, we have a receiver lab plus a junction verification lab. So all these things that we are in control, because if you are not in control of this thing, it's very difficult to operate even 1 or 2 telescopes, or not to mention the entire array. So, for example, for the receiver we are using right now, back in 2010, even though that we have the capability to develop it, but because we want to, we only have limited manpower, so we take advantage from all the ALMA development. So we used a 3 cartridge testing cross that from NLJ. We get the collaboration with Iran that sent us 2 Band 7 receiver. We obtained our 230 gigahertz from the Osaka Prefecture University. Ourselves, because the amoeba project, we are able to put together 86 gigahertz pretty quick. So that's save us tremendous effort so that we can focus on something else. So So now after we have finished the phase one we have 3 cartridge, 3 receiver band. Now the next step during this recent few years, we have time to develop the newer machine, a newer receiver band, newer cartridge. So that's our strategy of approaching this. And then the point from this, the experience that we learned is that some millimeter instrumentation it's difficult to come by. If you want to operate an array, you need to have a dedicated team, because usually a university group, they can prototype it, but it's difficult for them to dedicate to installation, to service, to maintain it. So that's the lesson we learned. Also, you need to have a strong collaborator, of course. So,
Yeah.
So 2 points. So our GLT experience that we try to convey our experience to this meeting. We're still ongoing because in the next few years we were working very hard try to move our antenna, 150-ton antenna over to onto the ice sheet, and then to building a observatory like ngEHT. I think you need to have a dedicated instrumentation team. So that's my talk. Thank you. Jim?
Yeah, it's difficult.
Tell us about the plan to move to the summit, please.
Plan. First, we are having a review meeting, external review meeting in September. That we will go through the science objective, technical details. They will let the external reviewer to give us the advice. So let's see. In principle, the antenna will be broken into 4 major parts. Each is one. Behind will be the receiver cabin with yoke of another, probably plus and then the third component will be the side container, which is housing all the electronics. And then there will be this support cone. There's 4 of them. We already have had planned how to pack it, put it on skis. We'll put it on skis and hold it up from. Well, first we need to get this part to a so-called transition point. The transition point is where land meets the ice sheet, and from there, to build a third row onto the ice sheet, and then push everything there, and then have the tractor to pull them up, 1,000 kilometers. Of course, and then there will be housing everything there. We need 8 power. But this thing will be the telescope will be sitting on skis. The reason for that expected cost right now, to construct the moving part about 20 million.
To construct the sled, $1 million.
Sled part probably $1 million.
So what is the total cost to reposition that?
20 million. 20 million.
Gopal?
So I had a question, 2 questions. One really a more short-term question. There was some talk about moving the antenna to a different location within the building, right? What's the time scale for that?
No, we don't have to do that now. We originally our agreement with the Air Force is that we have to we will disappear by next year. but then apparently we cannot. So we need renegotiate with them, and the agreement would be to until a few years later. I think the time is you know.
Second question, if I may, on the receiver cartridge that you showed, right now to switch between the bands, how do you switch between the bands 86? Is there a mirror that you put?
Well, at this moment, they are all sitting at category.
All right.
Right, so it's basically we just readjust the position of the secondary, but we are in the process to change it to add in 2 more receiver bays. So we will shift the VOBI receiver. So at that time we will have a mechanism at the top to redirect the signal.
I have a related question. You have these 3 receivers, right? 86 to 13, 3.5. Can you add 4 optics and dichroic to make for simultaneous observations, like people are talking about for NGEHT?
We've been thinking about this, but we don't have haven't had any concrete.
Yeah, we should talk with Esron. They did a study on how to do dichroics in front of on-star mixers.
Right. Good.
Oh, please go ahead.
Yeah, the Greenland ice sheet is melting, and I've heard that. But that's not a problem for summer, because it's still cold in the summer. But around the edges, that's made the ice very unstable, or so I've been told. Does that present any new problems and new challenges?
We talked to the traverse team. Now NSF decided to stop traverse. They don't want to do traversing anymore. That's NSF decision. So that is we were really opposed, were surprised to see that. So they are actually NSF actually expanding their summit station right now, building more houses. I mean, they're going to do it with airplane. But so we went back. First we thought that probably because the difficulty of or dangerous of going through the transition point. We went back to talk to the people that in doing that. That's actually a Colorado company. From their experience, they don't see any real issue there. You can imagine that there's probably more crevasses at the first 100 kilometer, but it's not something that's unconquerable, undoable.
That's accommodated by making the skis longer, I suppose.
Yeah, or be something like that. So we've been talking to this Colorado company. I'm also talking to our Danish partner, the Ice Core group. They have this E-Grip is doing ice core up there. From their information, of course, we approach the whole issue carefully. They don't think that this is a major obstacle, showstopper, so to speak.
One last question.
Yeah, thank you. Rather an ignorant question, especially in the instrumentation session, but why the high altitude is good for this kind of radio? Is it because it's good for cooling, or the atmosphere is cool enough to let the radio pass?
Oh, it's clear. It's at this kind of frequency, high frequency, it's the atmosphere. You have to get above the water vapor, mostly.
I see. So the atmosphere levels there are cold enough to let the radio pass.
The water vapor content is really low.
Right.
Thank you.
Thank you. Yeah, I'm not sure. Yeah, I know. No, we'll go ahead. We'll have Manuel Fernandez Lopez talking about the current status of the LLAMA millimeter observatory. Thank you.
Okay, thank you, everyone. Thank you, the organizers, for inviting me and having me here. Gave me the opportunity to give this talk. I'm coming from Argentina. My name is Manuel Fernandez Lopez. I work at the Instituto Argentino de Radioastronomía. We call it ER in Spanish. And I'm here on behalf of the LLAMA, the LLAMA organization. And we are trying to, yeah, okay. No, it's, yeah, I will skip that one. So yeah, so we are trying to raise a sub-millimeter facility in Salta province, which is that red region over there in the Argentinian map. It's a place which is 180 kilometers away from ALMA site, and it's in the north border of Argentina, or near, close to the north border of Argentina. And it's also at 400, more than 4,800 meter elevation. LLAMA stands for, okay. Let me talk about a little bit about the weather first. So as I said, it's a 4,800 meter elevation place, and you can see after five years of sighting tests, we came up with these opacities for this is the number of the month. So you can see that the opacities for the first quartile is kind of really low. It's comparable with the best sites on Earth, like Hawaii or in Baja California, San Pedro Martir, and Canary Island. Okay, so we are now. This project is a binational project. It's a Brazil-Argentina collaboration. Brazil has provided the antenna, so they were in charge of purchasing the antenna. The antenna is a vertex antenna, and Argentina is in charge of the infrastructure at the site, so raising the antenna, and both partners are supposed to get the receivers, the instrumentation, and get the maintenance and run the operations of the telescope. And so the management right now is starting to be built from scratch after several years, but we are mainly funded by two governmental agencies. Two of them from Brazil, FAPESP and University of Sao Paulo, and the other one is the government of Argentina, MINCIT. We have now a board of directors, which I am part of, and we have two directors, one from Argentina and one from Brazil, but we have not decided yet what's the final shape of our LLAMA observatory. We are trying to decide that, and this is a plot of the antenna, which is a 12-meter antenna like ALMA, but with two Nasmith cabins, so it's a similar thing to Apex. It will have 6 receivers, also ALMA kind receivers in the two Nasmith cabins, where we are plugging the receivers into two cryostats, and we are we are also harboring some instrumentation, invited instrumentation at the Sgr A. Okay, the surface and all the pointing precision is similar to the antenna of ALMA, and also the spatial resolution that they get with the single dish. We expect to get the same angular resolution. And we have also almost ready the optical telescope for pointing and the holographic system. We are building, well, in Brazil, they are building the transmitter, and we are probably borrowing the receiver from ALMA to make the holography. So this is not a new project. This is an old project that we are, well, the new guys from Argentina and Brazil are inheriting from the old guard guys, and the historical priorities of LLAMA project were to build to form part of an array. That's what the name stands for. LLAMA, which is double L, and we in Spanish we pronounce it like ye, and in Argentina we pronounce as shama. Okay, so you will probably hear it pronounced differently from Spanish speakers and Argentinian speakers, which also speak Spanish, but a different kind of. So shama or llama stands for Large Latin American Millimeter and Submillimeter Array. So originally it was intended for working with a small network of millimeter facilities, including ALMA and APEX. But the project has suffered a lot of delays, and now we are pointing to use LLAMA as a competitive sub-millimeter single dish, but also performing VLBI observations. We are also aiming for multi-band observations, so we will try to get some dichroics, at least one, but it's supposed to be two dichroics for 4 bands simultaneous observations. Yeah, and I think I will skip to the list to the next. So for the first light, LLAMA is intended to be working as a single dish. It will have a backend prototype that, as a minimum, we will have 4 gigahertz, but we are aiming for 16 gigahertz of bandwidth, and we are aiming also to make a band 6 receiver, which is already almost ready. The cold part of the receiver. We will be trying to purchase the warm cartridge to NREO, and we will probably have 2 more receivers, band 5 and band 9, and maybe another one which is being built in Chile, band 2+3. For first light, we will have only 1 Nesmith Kylin operative, and also, or maybe the band 2+3 would be installed at the Sgr A. During first light, we will have operations remotely controlling the antenna from at a place which is nearby of the site. It's the most nearby village, which is called San Antonio de los Cobres, and we call it SAC, which is a very high altitude place. But we have already a building over there to get control of the antenna. Regular operations will be that we operate the telescope from Salta City, which is the capital of the province. It's a nice and beautiful city. 1 minute, couple of minutes. All right. So, and well, we'll have also a percentage of open skies. We have in the past collaborated with EHT, but due to the delay or the problems with our project, we couldn't get the antenna working on time, and we are trying to convince our partners in Brazil to offer to the next generation EHT warranted time for use this antenna. We have a group at the yard, which is some of the people working with the yard is here from Argentina, collaborating in the development of the digital backend. And in the case we get as a member of the next generation EST, we will have to plug the dual receiver in the Sgr A or using our own device or with the dichroic to get simultaneous observations between band 6 and 7. The project underwent a complete reorganization a few years ago, like 3 years ago. We have an external evaluation that after which the Argentinian government reinforced and supported strongly our project, and the government has now new funding. So we are now in the path to build the antenna after hiring this company, which is called INVAP. It's an Argentinian company that designs and builds complex technological projects in the industry, and I don't know other. This is the transport of the piece the piece of the antenna that was damaged in a previous attempt to bring it to the site. LLAMA is currently at the implementation stage and is updating its science goals. We will harbor a workshop, a small workshop, but with an international panel in September. And the project expects to foster collaborations with international partners in science and technology. So these are the antenna parts that were checked by Vertex a few weeks ago. The parts of the antenna have been in those containers on top of the mountain during several years. I'm sorry, yeah, okay. I got some delay, but yeah, but apparently they are in good shape. So Vertex was very happy about that, and we are still have to take some decisions on the foundation of the platform of the telescope. But we have already a well-designed plan for building up a solar energy plant for supplying the 100% clean energy to this and other telescope which will be up there. So this is the place at San Antonio de los Cobres where we will control the telescope remotely at first, and then this will be a backup center for in case of miscommunication with Salta City. Our timeline is kind of getting to first light in like 2 or 2.5 years. This is very rough. This is a very rough estimate, but this is the plan that INVAP has in mind. At least this was a couple of months ago, and I think we are not very much delayed from this plan. We have well, we have doing this documentation and all the steps in L0, L1 requirements. This is something new in this project. This is something that we are learning, and it's taking a little bit longer than it would be. But we are new in this sort of big projects. And we will have another partner at the site. This is Cubic, which is a volumetric interferometer for cosmology. And some other projects are trying to or are looking for joining us at the mountain. So sorry for the delay, and gracias, obrigado.
Time for maybe 2 questions. Quick questions. Chen?
I was very interested to hear about the solar panels, the solar commitment to 100% of power. How many solar panels do you need? How well engineered is that system?
Okay.
Guaranteed will you be?
Yeah, I knew you would ask some questions about solar plant. So I asked the engineers last week, and they didn't provide me with a picture of the plans. So I cannot answer all those questions, but apparently the design has been finished. The government has this as a requirement for funding the telescope, and I think it's a major development for not only for the telescope but also for remote places in Argentina to provide the energy. And so they are more than 550 probably kilowatts peak, if you know what I mean. This plant would provide that amount of power, and that's enough for, at least with the current estimates, that's enough for JAMA and cubic telescopes. We will have a couple of generators, diesel generators, in case of any problems as a backup, but in principle we will be 100% green with the power supply.
So I think it's great.
Yeah.
Big fan of it.
That was one of the requirements also from the science part, to be as green as possible and as respectful with the environment as possible. Okay.
Gopal, last question.
So just as a follow-up to Shep's question, I think it would be really useful to get some of the details for ngEHT, also for remote sites. We are thinking along the same lines of solar power. And so some details on how you store the power, because most of our antennas will be needing to operate at night.
Why is that a problem?
Flywheel technology? No.
I'm not into the details. Okay. So yeah, I'm an astronomer, humble astronomer here, trying to present this thing. So the details will have to be discussed with other people. Yeah, sorry.
Oh, no, thank you. So the next talk is by Ganesh Rajagopalan. The Haystack 37-meter telescope is part of the EHT array at 230 gigahertz. Ganesh.
Yeah, good evening. Yeah.
Yeah, we're running a little.
It's running late, right?
Yeah.
So we heard about Haystack in Shep's talk and also in Michael's talk as a potential site to be included in phase 1 of the ngEHT. So here I am to talk about what we are doing right now and some funding from MSRA 1, the current ngEHT project. And I'm speaking in behalf of all the other colleagues at Haystack who contribute to this effort. And we'll start with it. Read. Okay. So you can see that with a 37-meter inside that radome. Is that point? Oh, this is yeah, I just need you.
Yeah, there we go.
So this is also forward, right? No? Okay. Yes. So we'll start. I'll start with a bold statement that the sensitivity of the Haystack telescope, 37-meter diameter telescope inside, can exceed the sensitivity of some of the current EHT stations, and the ngEHT project funds some of the development, a demonstration of telescope capabilities at 86 gigahertz via VLBA observations, and there's also a design study for 1.3 millimeter operation. And we have seen this other talks by Shep and Michael, and Haystack can really contribute to the establish critical transcontinental links. Also holds for GMBA, and this is a simulation made by our colleague Kazu, which shows that if you add Haystack to the ngEHT, you can improve the image fidelity by a factor of 1.4. And as I said, this can be a good addition to any array operating at millimeter waves greater than 86 gigahertz.
And we can use it as a VLBA station, and at other times we can use it for monitoring. Oh yeah, monitoring as a monitoring station. We talked about in the meetings here that it's not enough to just do once a year observations, but we need to have monitoring of the fluxes throughout. And there's also target of opportunity triggers. Not for me.
Oh, no, sorry.
Too early. Okay. And what is the sensitivity from a 37-meter telescope? So here I made this graph. Now, Haystack is, of course, here Boston, the city of Westford, 130 meter, 32 meters out. I mean, above sea level, but size really helps. So we heard about the 6-meter beam antennas being repurposed for ngEHT, sorry, ngEHT, not ngEHT, and then the 9-meter new dishes at other sites. So this plot kind of shows the theoretical SCFDs you can get, assuming certain receiver temperatures. I went to ALMA sensitivity calculator, put in the worst possible weather at ALMA, and it gave me 150 Kelvin system temperature for 230. I took that number, and if you have 40 to 60% efficiency, and these are the SCFDs in tens of thousands, and our telescope with 3 times worse system temperature, as in 3 times was at 450, and a lower aperture efficiency because we have the red dome and we have 100 micron roughly RMS. So you can see that even after all that, you get lower SCFDs like sensitivities that can really contribute in baselines with the small additions. It'd be a very good addition with this sensitivity. And my colleague Jens is a very preliminary model. He included the impact of receiver noise, the red dome reflections at different frequencies, and all with a PWB of water vapor of 8 millimeters over a few months. We can get several months at our site during the winter time. And here you can see the atmospheric attenuation curves. You were asking about, this is a lines oxygen here, water vapor, and it as go higher and higher, this value drops. So since we are at sea level, and this is the elevation of the telescope, you go through more sky when you go down in elevation, and so your system temperature increases mostly. And this is the IRAM 30 meter. It was prepared by Jens. He uses IRAM a lot for his research, so he knows all about 30 meter telescope here. So he made this plots to show that at 86 gigahertz, you're pretty as good as IRAM. And this is the Greenland telescope. We picked the values from the web and showed that at 86 and at 230, we could be almost as good as GMT. And it's a very modern telescope design. It underwent a huge refurbishing effort completed in 2013, funded by United States Air Force. And it's got a new backup structure and a brand new surface, and 75 micron surface accuracy designed for radar operations up to 100 gigahertz. It's a very fast slewing antenna, and I don't know how many of you played with the rock spinning on water thing. This is also spins on hydraulic. It floats, and it's got a hydraulic pumps, and it can slew very fast, can move from one part of the sky to other in time. And pointing and tracking accuracy has been measured to be better than 1 milliard degree, which is 3.6 odd seconds. The operations model is that it's used every day by US Air Force during the day. But it's available after 11 p.m. for any astronomy work. And it's also available on weekends. And again, for special campaigns like EHT or GMBA, Colin is here, so we can have a very cooperative agreement with the Lincoln laboratory that is running the telescope radars for defense mission, and we can get more time during the campaigns. So the primary maintenance is like a low-hanging fruit for the project. Its primary maintenance is paid by the defense mission. So astronomy has to only pay for any engineering we need to do, equipment and operators. And this one is on the backside. This is a picture of what it is inside. That's a receiver box that comes down once a year, brought down by Lincoln Labs for maintenance work. And it has got a sub-reflector on hexapod, so you can select different receivers. The astronomy receivers are vertically aligned. I have another picture to show. And it's been around for bigger people in the crowd. It's been around for a long time. So this kind of, two references I gave, that talks about the very first upgrade to 3 millimeters in the 90s, and then we are talking about another upgrade to 3 millimeters after the refurbishment. Then the authors of two authors of this paper are in this audience, and the audience also has people who have used this telescope for their research when it was radio observation. And ongoing activities, selected ngEHT activities are these: improvement to the W-band signal chain, installation of VLBA equipment to do the to establish VLBA capabilities, tag-along experiments. So far we have done at 86 gigahertz. The design of a 230 gigahertz system for the phase 1 proposal, and then we also have on site we have the ngEHT IR water vapor radiometer. This is on the near the Westford telescope, right where the GPS on the GPS tower. So we have GPS data as well as IR data for recording the site weather parameters characterization. Apart from these, we have several selected internal activities to improve the overall system. I'll move forward. And this is just shows the diagram system overview where there's a color coded to show what is MSRI1 ngEHT is funding and what was existing before, and some of the internal activities for improving the brand new telescope control system software. And keep going. The new low noise amplifiers, very wide band, 65 gigahertz, 116, and we had placed an 8 gigahertz bandpass filter for single sideband separation. But eventually, we would like to have a sideband separating system with almost 30 gigahertz of bandwidth. Telescope control system is new, and we have developed a COTS-based GPU backend. And this shows continuing improvements in the T system. This is where, when we did the last tag-along VLBA, got fringes to VLBA antenna in 2016. That's almost like 500 Kelvin. And then now it's around, it's still, not state. We have the state-of-art amplifiers, but we still have system improvements to be made. This is about 150 Kelvin. And this is where we have, I think Chip asked the question in one of the meetings. You have space for the 230 gigahertz receiver, and this is identified space for the 230 gigahertz receiver. And that's a W band. This is a Q band, existing Q band receiver. These are all legacy receivers from the old times, K, Q, and W. And of course, now Sarah is here. So if 86 becomes part of the ngEHT, we'll definitely go for a dual band EHT 230 and 86 gigahertz receiver here. And so you can't see I have there. The combined K and Q also can be combined. I've been talking to our Korean colleagues, and we did the VLBA observations recently, and using the standard VLBA setup like RTBBs and Mach 6 recorders. We got fringes to ALMA under the APP test last few weeks. We also tagged along the GMBA run in April, and analysis of data is ongoing. We're waiting for initial data analysis to happen at Bonn. I was talking to Thomas yesterday, so things will happen before the next campaign in the fall. So we have more comprehensive testing planned, and these are the plans for 2022. We have to get a very good point model, gain curve for the receiver, and then we are also upgrading the K-band receiver, which can be used when the weather is really bad. So, and this must be the last slide. Okay, we have very ambitious goal to support different sponsored programs as we improve the receivers one by one. Also, bringing the more user community, and also develop a science case, develop educational case, ask for more funding. I'll stop here.
What's the pointing accuracy?
Blind pointing was 1 millidegree, that's 3.6 arc seconds. 3.6 arc seconds.
Satoki?
About the induction, the radar to the high frequency.
Yes, we have a model for the radar. It will reduce the apparent because it's like a reflector. You have a trick. You're plotting some figure. If you assume a reflection coefficient 1 minus gamma squared. And then we're waiting for Gopal to do the 230 gigahertz hot and cold load testing. When that happens, we'll go with our actual hydrophobic coated panel. We have panels to test. So we will test Gopal's receiver with and without the panels to see how much.
So the transmission was already measured for you.
Yes, I have that data too. Yes,
That's pretty good. I mean, we need to do it with the pieces to really find out, but transmission was reasonable.
Yes. Those data were used by my colleague to do that simulated model where you rolled in detection to the radar.
Oh, Remo?
Yes.
Okay. Great.
Okay.
Sorry, we're running a little behind time. The last one is Noemi La Bella on the African extension to the EHT.
Yeah, I'll try to be fast and let you take your coffee. So I'm Noemi, a PhD student at Harvard University, and yeah, I would like to present this project that is it has the importance of the African station to the EHT in producing movies Extraterrestrial. Okay. That is the African millimeter telescope. I don't know what happened there, but so the African millimeter telescope, as probably you know, it will be the first millimeter radio telescope that will be in the African continent. It's planned to be built in Namibia on the Gasberg mountain, and this is a strategical position, in particular in imaging Sagittarius star, because it's located in the southern hemisphere, and also it is in the same latitude as LLAMA. It's a good site in terms of water vapor. There are no absorption by the water vapor, also at 1.3 millimeter. And this is not the only site that we want to build in Africa. There are also other potential sites, like, I don't know which is the point. Okay, like Canary Island de La Palma, in Kilimanjaro, and on the Grasberg mountain. And so this can generate a potential African array to the EHT. So something is happening in this presentation, but it's fine. Why we are interested to add the telescope in the African continent, because as you can see, the most of the stations are located in the western part of the array, and to the moment we are able to reconstruct variable source just using a window that is in the western part of the array, but not with the eastern array. And so the goal of this project is to show the impact of the African array that consists of these two stations, the African millimeter telescope and the Canary Island telescope, to the EHT in producing movies of Sagittarius star. We use these methods, as was also mentioned this morning by Michael Johnson. We can test the capability of the array by producing synthetic observations. And so we produce the GRMGD synthetic data with SIMBA, also the synthetic data with the EHT imaging, and the movies with the dynamical imaging algorithm. All right, so first of all, we looked at the UV coverage. This is the, in blue, there are the 22 EHT baselines with the current configuration. In red, there are the additional ngEHT baselines. In particular, very important are the long baselines with Arizona, so we can increase the resolution of the array. And in brown, there are the Canary Island baselines. So here, very important, the short baselines to catch the diffusion emission. But we are interested to see how this UV coverage evolves in time, because we want to see where we have a good window to perform dynamical imaging. So for this goal, we built the Fourier filling factor plot that it look at how well the UV plane is covered in terms of area. In particular, here we use the normalized filling factor to the maximum filling factor with the 22 EHT. And this is our threshold that corresponds to the 70% of the maximum of the filling factor with the 22 EHT array. So this means that we have good windows when we have the filling factor greater than this, higher than this line. So with the current EHT array, we have a good window to perform dynamical imaging that is located in the western part of the array. But if we had the African millimeter telescope, then we have 3 more windows to perform dynamical imaging. And if we had the Canary Island station, then we have like a 7-hour of window, potential window to produce our movies. So in order to produce our images, I split the array into parts, the eastern array and western array. As the eastern array meant when we have the Africa station that observes the Sagittarius star. All right, so these are okay, but the important are the images, so it's fine. These are the images that we obtained. This is the, I don't know probably what happened.
You go on, we try to make it a little bit smaller. But
I think it's the mod, yes.
okay, I wanted 90%, but there's no 90%.
Make it 50 is fine.
50?
Yeah, I think it's,
That's
really small.
Fit to window.
Oh, okay.
It wasn't fit to window.
Okay, so thank you. Okay, so this is the geometry simulation, the average image. Then we have the image, the average image with the eastern array, but without the African station. And this is the result. Basically, we don't have the coverage to have a good image of Sagittarius star. But if we had the African millimeter telescope, this is the result. There is an increasing improvement of the quality of this image. And if we had also the Canary Island station, then we have a less noisy image. And here we report the host of the image that we obtained with the Western array. In order to produce our movies, we produce the image using the wall array. So these are the images. This is the 22 EHT image without the African stations for the whole array. And it is instead the image that we obtained with the 20 EHT plus Africa. So you can see that the quality of the image is very good if you compare with the geometry simulation of the image. So we use this one as prior for our dynamic imaging. And so these are some snapshots that we took from our movies. In the first row, there are the model snapshots that are taken in the eastern part of the array. Then there are our reconstruction with the eastern array plus Africa, of course. Then we have again the model snapshot, but this time in the western part of the array. And those are the respective snapshot that we have with the east-western array. So we can see that the eastern array plus Africa produce a very good reconstruction, dynamical reconstruction of Sagittarius star if you compare again with the model. We want also to study the variability of Sagittarius star and see if we are able to catch some variability. But from the geometry model, this was not possible because we are too much dominated here from the average image. And also because in geometry simulation, we don't have a coherent motion that we can follow. And so in order to do that, we use a simple model, a split movie that, okay, it worked, nice. Just that movie, and so this is the ground truth. So this is the model movie that we have. And then this is the movie that we obtained with the Eastern Array plus Africa, and then the one with the Western Array. And again, from here, we can see that we have a good movie with the Eastern Array plus Africa, things that we cannot have without the Africa station. Actually, we did more analysis on these hotspot movies. Okay, first of all, we looked at the flux profiles. We reconstructed pretty well the flux profile. So these are some snapshots of the model movie. And these are the flux profile that was extracted by the image. So basically, we extracted pixel by pixel the flux profile in function of the angle. And what we can see from this curve is that the Eastern Array plus Africa, but also the Western Array, reproduce quite well the trend of the model. And in particular, the location of this hotspot is quite well reconstructed. Another way to show it is by doing this other plot, that is the rotation of the reference group, where again, it's a way to see if we reconstruct the hotspot motion. In this case, we compare the first frame of the movie with the frame 5 slides later, and we was searching for the angle for the rotation, basically by using a metric that is called Sgr A. And this way this was applied for all the frames, and we obtained a distribution of angle in function of the time. So here, when we have the peak, we have like the hotspot, as we can see from here. So when there is the hotspot, and is that when there is zero rotation, is because we don't see the hotspot, as we can see from here. And so what we can see is that with the Eastern Array plus Africa and also with the Western Array, we reproduce quite well the motion of the hotspot, and actually with the Eastern Array plus Africa, this is quite much better reconstructed. Okay, so I will leave the summary here, but I think the message is clear. The African millimeter telescope alone will increase significantly the quality of our average image, our dynamical reconstruction. If we would like to study the variability of Sagittarius, for example, there is a flare during the first hour of observations, we are able to catch it with the African extension to the HT, so with the Canadian telescope and the African telescope. Thank you.
Questions? Chen, please.
Don't take this the wrong way, but why are you calling it the African millimeter telescope?
Why do? Sorry.
If there's more than one site in Africa, why is this particular site called the African millimeter telescope?
Why chose the African millimeter telescope in just simulations? Do you mean?
No, the name.
No, the name. Why the name African millimeter telescope? Oh wow.
No, because the name is still for sale.
Oh, is it? Okay. What will the other African sites be called?
KMT, Kilimanjaro.
It started with a study on African millimeter telescope. This is essentially AMT1.
NMT, Namibia millimeter telescope. Namibia, NMT is a nice name. KMT will be another name.
But it will get Haystack will get
I know that when the Japanese launched the telescope, you get the new name as soon as it launches.
Yeah.
So maybe that's
something like that.
Yeah.
Well, at least, I mean, do you want the DMT?
Actually, my name is not for sale.
Yeah, I'm glad that at least you mentioned that Kilimanjaro is.
Yeah. Yes.
So we are still fighting for that.
That's nice because
so I think a lot of these applies. I think we have not been able to make the simulation yet, but we're still in a process of measuring the verification and cycles.
That's very nice because I produced lots of simulation with the Kilimanjaro.
Okay.
Yes, I also. I'm not there, but I did also. So this nice.
Any more questions?
Everyone is ready for coffee.
Okay, Thank you again. Sorry, Jan, a little bit late. My apologies. Very nice. I only want to get on that.
I was like, right. I was.
Yes, yes, that's very important. Yeah. Please bring your slides. So, please.